Hello, hello. Welcome back to the lab. Welcome back to EEforEveryone. I'm so excited that you've tuned in to part 6. Whoa, part 6. I can't believe that it's already part 6 of our series titled What Even Is, where we've been diving into current sources. We started with just the fundamental theory of what is a current source, and we've been building that up piece by piece, building it up block by each. We started with a transistor current source, made that regulate with an OpAmp, and then we added in an integrator and a difference amplifier. Well, today it is time for the next piece of this saga. Check out the playlist if you haven't seen any of those, but otherwise we're going to dive right in to where we're going today. That is PID control, a proper controller, a proper compensation network on this. It's more of a controller, less compensation network. Compensation network would be more like type 2, type 3 compensator. We're going for PID control scheme. Pretty fun stuff, pretty fun stuff. Let's dive in. Like I said, we're really building off of where we left things last time. So yeah, we've got our integrator, we've got our error amplifier, just like we showed you last time around. Let's add a couple more pieces to this puzzle. Let's start with the P term. The P term is quite simple. This is proportional. So the integrator took a constant error input and turned that into a slope. It took a constant error input and turned that into a rate of change over time. Now, what's going to happen with our P term? It's going to take a input and it's going to amplify it. So depending on the gain of our P term, it might amplify it by a factor of 2, 3, whatever we want it to be. It's a P term. It's a proportional term. And based on the weight of the P term and the I term, it will change the transient response of the system. So how do we do this? Well, if we're going to keep everything non-inverting, we just build a simple non-inverting op-amp amplifier. It's really that easy. We do that with a positive and negative input. The positive is directly our input. The negative term has a resistor going to ground. Ooh, running out of space. And then the resistor coming around to the front. Then that's our output. Phenomenal. By the way, for those that might be able to hear that, not sure how tuned my mic is. That's the pupper next door, currently going through heat. Bad time, sad time. He gets a little grumpy every now and again, but that's okay. What about the D term? The D term. This is the differentiator. When the input does this, the output is this. It's amplifying the rate of change. So the entire time, the slew rate is constant and increasing. The output is some positive number. When change stops, it has a 0 term. So it's only impacting the loop during moments of change. And the excellent thing about this term is that as the slew rate increases or decreases, that's how we get a positive or a negative impact. So that's how the differentiator works. And much like the integrator, the differentiator will function by adding a resistor and or by charging capacitors. That's how it works. But rather than pumping current through, well, you'll see. It's pretty exciting. I won't try to paint it in a word picture. All right, let's draw this differentiator. Now, this is actually going to be a differentiator with a filter built in. Real differentiators without a filter, unfiltered differentiators, have this nasty tendency to be incredibly unstable. And so we're going to add a couple extra resistors to this differentiator to make it both non-inverting and to make it a little more stable. All right. It's basically filtered. It's a filtered differentiator. And we're adding a gain stage at the end, and we'll get to that in a moment. We're going to start with our input. We get our capacitor, and this comes into the non-inverting input. Sorry, to the inverting input. The non-inverting input goes to ground. Okay, so basically what happens is we're going to get an input on this inverting input whenever the input voltage changes. Whenever this is held constant, the bias point of this node will just be 0. That's all it's going to be. Super simple, super easy. But then there's kind of this weird thing that happens where depending on this resistor value and that resistor value and these capacitors, changing any of these components, the capacitor, the resistor, it changes both the wave shape because we're like filtering the input signal and also the amplitude. So if we want to have a way to only modify the amplitude, what I like to do, and maybe this is just me being lazy, because we already need to invert the signal, what I will do is I will just add an inverting amplifier stage at the end of this. So then we do that by adding a resistor, hooking that up to the inverting terminal, non-inverting terminal to ground, and a gain resistor. So then that becomes our output. So that's one way that we can scale the D terms. That will allow us to modify the amplitude, invert the signal again to get it back to the correct polarity, and give us something that we can add to the summer. Pretty fantastic. So we have our differentiation, we have our integration, we have our proportional. We've got the 3 fundamental pieces of the PID controller. Now, how do we combine these? How do we use them to work together? That is where we need the non-inverting summing amplifier. Phenomenal. How do we do this? Okay. Now, in order to make this summing amplifier, it starts a lot like a non-inverting amplifier. You've got the output, you've got a resistor, you've got a resistor, this goes to ground. And we're going to put the negative input on the top. That comes right there. On the positive input, rather than just connecting one source, what you do is you branch this out and you add resistors. If you want to have a gain of 1 for this type of amplifier, you set all of your resistors to the same value. In this case, that's not what I'm going to do. I'm going to set that to 20K, 10K, so we should have a gain of 3 if I'm doing my pocket math correctly. And then what you end up at the positive node, the input, is the average of the 3 inputs. So you have in 1, in 2, in 3. Now, you might ask, why did I make this output have a gain of 3? Why did I want to have a gain of 3 on this amplifier circuit? Well, because the differentiation term is 0 most of the time. The proportional term is 0 most of the time. And the integral term is going to be divided by 3 most of the time, because we're going to have, let's say we have a 10K, 10K, 10K. You got 10K, 2 10Ks in parallel, so basically 5K. That resistor divider will divide your voltage by 3. And so if I want the integral term to still have the same impact, the integrator to have the same impact that it should, I need to amplify the output of this summing amplifier. Then, of course, we need to scale the other 2 terms appropriately. Another way that we can achieve some scaling is by adjusting the weights of these 3 resistors. There's a few different ways that we can change how this behaves to tweak its response. This is the summer. So this is every fundamental block that we're about to integrate. We're going to have an error amplifier, the integrator, the proportional, and the differentiator blocks. They're all going to come into the summer, and then the output of the summer is what we're going to connect to our MOSFET. This is going to be fantastic. Let's take a moment, switch over to LT Spice, capture this, and keep on moving. Here's that difference amplifier again. We've got the difference amplifier amplifying the error. It's our error amp. Now we've got our D term, our differentiator, captured right here. We've got our integrator. We've got our I term captured in the middle. We've got our P term up top. These are equally weighted at the summer with that gain of 3. Our P term is set to 3 as well. The I term you will see functioning. It's the same as it was in the other integrator. And the D term, we will take a look at how that looks. Right now we're just doing the step response. So that's pretty fantastic. And let's run the simulation and see how this looks. Okay. what do we see? What do we see? Well, we see there's still a bit of delay. In fact, perhaps more. We've got a little bit of overshoot. It settles out pretty quickly. Basically, that tells us is that we're overshooting. The biggest reason why I think we're overshooting is because our D term is pretty strong right now, which means that if we look at the summer, what's coming into the summer, and therefore out of the summer, it gets that big surge that kind of gets us up closer to where our MOSFET is enhanced, and the rest of the control loop kind of catches up in a moment. We can see the D term's response to the error term, right? The error term increases a bit. The D term says, whoa, now we need to get up there. But since it's filtered, it doesn't quite snap. It kind of gently moves. As we're held constant, that term comes back down to 0. And then as the error comes down, the D term pulls back on our controller. The I term responds how we would expect, slowly increasing over time until the error is taken out. You can see that since we overshoot, the I term settles down a little bit. Then the P term is really quite simple. The P term is just the error multiplied. It's really that simple. Just take a scalar multiple of the error. Pretty fantastic. So in the summer, takes the input, multiplies that a little bit, and that just makes sure that we don't run out of volts, because 10 volts divided by 3 is not a whole lot. That's not leaving much headroom for the integrator to actually enhance the MOSFET and get us moving. Okay. So what might we do to increase the transient response? Well, for one, we can increase the I term. We can make the integrator respond a little faster. We can increase the P term. That should make it respond a little faster. And we can actually increase the D term as well. So let's try setting this to maybe 40K. Let's try that to 40K instead of 20K. And perhaps let's set this to 2K instead of 1K. Let's take a look at how that responds. Okay, might have made that integrator. Oh boy. I think we might be a little unstable, folks. Perhaps I turned this up a little too much. Let's try 1.5. Still? Maybe it's the P term. Okay, it must have been the P term. Let's put that back up to 2K. Let's get our integrator cranked up. There we go. There we go. There we go. Okay. You know what might be fun? Do you know what might be fun? Let's do some parametric sweeps of some of these parameters. Yeah, I'm gonna get that set up. Let's come right back. So what we can see when we tweak that resistor, we're tweaking that I term resistor from 1K to 3K in 1K increments. That lowest resistor value provides the fastest transient response with a little bit of overshoot. But if that's what we want, if we're really shooting for aggressive transient response and we don't mind a 5% overshoot to respond twice as fast, well, hey, let's keep that. Let's keep that 1K resistor and try tweaking a different value. We're going to apply that same step to our D term. So now with our I term kept pretty snappy, let's run 3 steps on the gain of our D term and look at what our options are for transient response. Okay, looks like our simulation has finished. And what we can see is changing that D term really changes that wave shape. It changes how we land. It doesn't necessarily change the settling time, but it appears to adjust how much overshoot we have. And, well, I kind of like reaching our set point fast and having a tiny bit of overshoot rather than... Yeah, so let's go for that center curve. Let's go for 2K. I really like how 2K looks for our differentiator. What about our P term? Let's take a look at that P term. Okay, we've got it set to take some steps of gains varying from 2 to 4. And we're going to take a look at how our system responds. Is that already done? Wow, that's already done. Okay, those curves might be a little too close together. We can't really see that. Okay, let's maybe expand the range a little bit. Let's go to 50K and let's do 10K increments. I was hoping that one of those was going to be a little bit unstable. Apparently, I did not get that lucky. Okay. Here's our first step. Looks good. Let's get our next step. I think we found one that's going to be unstable. The simulation is taking a long time to run. Yes. Yes. Good old instability. I love it. Okay. This is going to take a little while for LT Spice to sketch. I'm going to see if I can get lucky and zoom in here. There we go. So this brings up something very important, and that is gain and phase margin. Gain and phase margin is something that we haven't really gotten into, but obviously, as you might imagine, if the phase of our controller is approximately the same, and we keep increasing the gain, eventually we will get to a point where our loop is either marginally or completely unstable. In this case, it looks like that was run 4, so that was a gain of 5 is where this controller became unstable. Yeah, let's keep this relatively tame. Let's keep it at 20K. That is a gain of 3. So, with our gain of 3 fixed, our D term kind of locked in where we like it, our I term in a pretty good way, let's run the simulation again. Should just have a single run. Let's view the transient response. Look at that. That's a pretty small overshoot and settles pretty quickly. I like that quite a lot. Let's look at our current. Yes indeed. Settle out at 10 amps with a incredibly high degree of accuracy. What are we at? We are at 9.9994 amps. Here, let me get that pulled over here. Look at that. Quite good. And we notice there are some little hiccups in the current when the load has one of those transient events. However, the current is quite constant. It never really gets much further away. I mean, it goes from 10 to 10.011. So even in a very drastic, that's like a 100 volt transient on the output. So that would be if our compensator, if our controller did nothing, the difference in current through that 1 ohm resistor would be 100 amps. And our controller was able to keep that within 0.011. So we've got pretty snappy transient response. Though, now that I see this value, I can't help but notice it's going a little too slow. Let's run that again with the faster transients. There we go. So now we're seeing transients of about an amp in that controller. A little bit of instability. Some ringing. I wonder where that might be coming from. Well, let's take a look at our D term, right? So we get that initial turn-on event where we'd expect the D term to have a value for a little while. And then we have these... Ooh, that's some oscillation. That looks kind of similar to the oscillation that we saw in the output. Well, because when we look there, okay, so that's... Yep. And then we look there and... Yep. It's not... Oh, wow. Look at that. Okay. Just sanity check. Let's remove our D term from the equation. Let's just cut that trace. Let's rerun the simulation. Let's look to see how the controller responds. Let's see if it was really coming from the D term, or if I was just blaming it for something that was not its fault. Looks like there's still a little bit of that nonsense. Looks like it's coming from our P term. All right. I'm convinced. I'm convinced. Okay. Still didn't quite get there. However, thankfully, it's because our I term is still cruising. Our I term is still getting lower. The gate voltage is still going down. It's just hard. It's hard to drive something designed for 25 amps down to such a low current. It's almost as if someone desiring to have high precision at low currents could have multiple stages where you might have one FET designed to go from maybe 0 to 5 amps for that high degree precision. Then you have your high power FET designed to carry it from 5 amps up to 100. And then you can use those in combination, or maybe you've got some FETs that can go to higher voltage, some FETs that can go to higher current, and then you auto range between them and just kind of drive control loops on all three with some kind of controller that's behind the wheel. Man, that sounds like that could work. Where you just kind of fade between different current control loops. I've got some big plans. I got some big ideas. If you might be picking up on some of this dreaming going on over here. Perhaps we'll use a PID loop in hardware. Perhaps we'll use PI controller in hardware. Perhaps we'll do some fun things with DACs and isolation and all kinds of funness. A little bit of software in there, maybe? I don't know. We'll see. We'll see how motivated I'm feeling. But for now, this is pretty exciting. Now, this might look very promising. Now, if we even threw a linear MOSFET instead of a switching MOSFET, this could work pretty darn well. I really love this controller. Basically, we just have a PID controller connected to an error amplifier that happens to be monitoring a programmable threshold. Perhaps that was coming from a DAC. Perhaps that's coming from a voltage source. Perhaps that's coming from a resistor divider. But wherever that reference voltage is coming from, there's a reference voltage being compared to a current shunt, and then that is coming into this controller and ultimately driving a MOSFET. Like I said in that rambling, there's a few things that we might be able to do to turn this into a pretty sweet electronic load, but we need to stop thinking about a current source driving something, and we need to start thinking about some nuances of being a current sink. For example, when that 1 ohm resistor goes away, if we, for example, had no load on the input, and then we suddenly connected 100 volts, which never do that, that is unsafe. You should power everything on where you're not touching it. Don't do that, so you'd get a nice ramp. But anyway, let's say you did that. Let's say we put a harsh load step by applying a constant voltage source or a charged capacitor bank to a MOSFET, right? What would our control loop do? What would our control loop do? Well, let's think about that for a moment. 0 volts on the input. We provide a reference. What happens at our MOSFET? We're fully enhanced. We're up at 10 volts. That means that our ESR on that FET is like a milliohm, a couple milliohms. What happens when you apply that voltage source? Current. Until your control loop can pick up and actually figure out what's going on, there's going to be that brief moment of time where you could really vaporize that MOSFET. Oh, sorry, I wasn't showing you. Yeah, we're up at 9 volts. We're up at 9 volts. So you could really vaporize that MOSFET, and that's not how I would want my electronic load to work. So perhaps there's some circuits we can add to this. Perhaps there's something we could do to tweak this design to make it a little more fault tolerant too. Maybe we can bound the upper voltage. Maybe we can add some kind of transient over current protection. Let's think about how we might tweak this design to improve it. All of that coming in the next video, the last episode of What Even Is. Obviously, we're not done talking about current sinks, but this is meant to be the core, the fundamental, the introduction to current sources. So this will be the last episode of this fundamental theory of current sources and current sinks, and we're going to be kicking off our new series on the electronic load project very, very soon. I can't wait. I'm super, super excited. Okay. If you like this video and you can't wait for more, don't forget to hit that like button, get subscribed, or check out some of our links in the description. You will find this simulation file linked there, along with a link to our Patreon page. Thank you very much to those who have decided to support us directly via Patreon. Y'all are fantastic. Thanks for keeping this possible. All right, most of all, I hope that you learned something great today, and I hope to see you again soon. So thanks for watching EEforEveryone, and thank you for staying till the end. Bye.